Hello and welcome. Now, in this video, I'm going to look into how serial transmission is achieved with the ATmega 328. Introduction. Now, there are two ways microcontrollers can communicate with each other. Now, the first method, as shown here, is what we call parallel transmission. Now, as you may have noticed that in parallel transmission, multiple bits are transmitted or sent at the same time. Now, however, the downside of this is parallel transmission requires a number of wires or conductors. Now, this makes them expensive to implement. The second method is the serial transmission. Now, in serial transmission, the data is transmitted one bit at a time over a single wire. Now, I know I've shown two wires here, or two conductors, or two transmission channel. The thing is, one is to send the data, and the other one is to receive the data. Okay, now with the serial transmission begins with bit 0, or in this case D0, which is the least significant bit, and then the rest of the bits that makes up the character follows on. Now, so here we have D0 or bit 0 followed by bit 1 or D1 and so on. So the last bit here is D7. Now, the binary pattern here represent the uppercase I, character uppercase I. The 49H in brackets, that's 49 hexa. That is the hex equivalent of I, capital I in ASCII code. Now, what I've done here is I've added two extra bits. The first one is the start bit, and the other one is the stop bit. Now, the start bit basically indicates that's the start of the character. And the stop bit, you might have guessed, that indicates the end of the character. So if you're transmitting the uppercase or capital I character, you send these binary bits, and on top of that, you need to add these two bits. Now, this start bit and stop bit must be added to each character. Now, the role. So what's the role of this start bit and stop bit? Basically, the role of the start bit and stop bits are used as the means of timing or synchronizing the data. Now, this is for asynchronous transmission. Now, by asynchronous transmission, what it means is that the two devices that are transmitting and receiving from each other, basically each microcontroller or two devices have their own unique clock signals. Now, with the synchronous system, both the controllers will share a common clock signal. So in this video, we are focusing on asynchronous transmission. Now, in serial transmission, what happens is that the start bit is sent first. So the start bit will be the first bit to be sent, followed by D0, the least significant bit of the character, then followed on by the rest, and then finally you have D7, and after D7 you have the stop bit. So stop bit will be the last bit to go. So let's take a look at the ATmega 328 serial communication. Now here I have shown the block diagram of the ATmega 328 microcontroller. And the ATmega 328 microcontroller supports three forms of serial communication. The first one is the USART or the universal, synchronous, and asynchronous serial receiver and transmitter, USART. The second one is the SPI, or serial peripheral interface, SPI, and then TWI, two-wire interface. T for two, and the W is for wire, and the I for interface, TWI, two-wire interface. So these are the three forms of serial communication supported by the ATmega 328. But in this video, I'm going to focus on the USART. Now, the USART basically consists of three parts. The first part is the clock generator. The second part is the transmitter. And the third part is the receiver. And by the way, as you notice, this is a block diagram of the USART. Now let's focus on these three pins here, or the three input and outputs. The first one here is the XCK. This pin here basically controls whether the clock source is internal or external, and it's on the port D, bit 4 of the ATmega 328, and it's pin 6, which is this pin here. Then the TXD, that is the transmitting pin, that is on port D, bit 1, pin 3 on the ATmega 328, which is this one here. Then the RXD, that is PD0, the port D, bit 0, that would be pin 2, that is up here. Now, as mentioned earlier, the USART has three parts: the clock generator, which is this one here, transmitter, receiver. But now, what I want to do is to focus on the registers attached to each of the parts. So for the clock generator, the registers that I would be interested in would be the USART baud rate register, or UBRRN, which is this one here. And for the USART data register, transmit and receive, or UDR, the transmitter and receiver has their own UDR. So UDR transmit is here, and UDR receive is on the receiver side. Then I want you to take notice of this three register, which is the USART control and status register, or UCRS. Now there are three separate UCRS here. One is UCRS A, the other is UCRS B, then the third one is UCRS C. Programming the USART. Now, a few moments ago, I mentioned the registers that are linked or associated with the USART. Now, I'd like to take a closer look at these 5 registers. So the first one is UDR, or the USART data register. Then there is the UCSRA, or USART control and status register A. Then the UCSRB, USART control status register B. Then there is the UCSRC, USART control status register C. Then finally, but not least, there is the USART baud rate registers. Now this is a 8-bit, these are two 8-bit registers. So the first one is UBBRL, L for low byte. Then there is a UBRRH, H is for high byte. Let's take a closer look at these registers now. So the first one that I want to look at is the UDR, which is the USART data register. Now, the USART data transmit data buffer register, which is this one here, the TXB, and then the USART receive data buffer register, which is the RXB, share the same I/O address. So although these are two 8-bit separate 8-bit registers, they are sharing the same address. Now, what I've done here is come up with a simplified diagram. Actually, well, I should strictly say I adopted it from this book, the AVR Microcontroller and Embedded System Using Assembly and C. So I adopted it from this book, and I find it useful. I hope you do. So let's take a closer look. So these are the two registers that I mentioned earlier, the transmit data buffer, TXB. Then there is a receive data buffer, RXB. Now, the data that you want to transmit, you put it in this TXB, the data buffer register. It is then sent to the transmit shift register. So parallel data goes in, this shift register will shift them out 1 bit at a time via this pin. And this pin is the transmit pin. And the data that you receive via this pin, the RxD pin, the data comes in here in serial form, goes into the shift register convert that to parallel form, and store it into the receive data buffer register. Okay, I hope that's clear. Now let's take a look at the next register, which is the UCSRA. That is the USART control and status register A. Now this is an 8-bit register, but I want to focus on this bit here. Bit 5. Remember, we start with bit 0. So bit 5 is the USART data register empty bit. The E stands for empty. So this is the bit that we want to focus on. We will be doing the programming later on. You'll see how this works. So basically, this bit is a flag, right? This is just a 1 bit. Indicates that if the transmit buffer, the UDR, as mentioned earlier, is ready to receive new data. All right, so that's the role of this bit. And if the UDRE, which is this bit here, is logic 1, that indicates that the buffer is empty. And if it's empty, it is ready to be written. That means ready to receive data. Then next one is the UCSRB, the USART control and status register B. Again, this is an 8-bit register. Let's first of all focus on bit 3. Right, bit 3 is the transmit enable, TXE, transmit enable. Logic 1 enables the USART transmitter. So if you put a 1 here, that means the USART transmitter is ready. If it's 0, then that disables the USART transmitter. Now, I'd like to draw your attention to bit 2. Now, I'll talk more about this in a few moments. So just want you to take note of this for the time being. Okay, so the next one is the UCSRC. That is the USART control and status register C. Again, this is an 8-bit register. I like to focus our attention on bit 1 and bit 2. That is the UCSZ. Let's look at this one first. UCSZN0. And then this is the UCSZN1. Now, these 2 bits are combined with UCSZ2, which is in the USART register, which was mentioned a few moments ago. Remember, I highlighted that bit. So these three, the combination of these three bits, this bit here from the UCRSB, and with these two bits here, that would determine or set the number of data bits or the character size that you want to transmit. Okay, so what I've done here is I summarized the character size with the different combination of UCSZ bits. So these two bits here, the UCSZ0 and the UCSZ1, they are from UCSRC register. And this bit here, the UCSZ2, that's from the UCSRB register. So the combination of these three bits will give you the character size. For example, let's take a look at the character size of 5 bits. Then you need to set UCSZ0 to 0, UCSZ1 set it to 0, and UCSZ2 you set it to 0. With this combination, it will give you a character size of 5. Now, in our demonstration in this video, we'll be using a character size of 8. So the combination would be UCSZ0 would be a 1, UCSZ1 would be a 1, and UCSZ2 would be a 0. That will give, this combination here will give us a character size of 8 bits. Now, what I've done here is I have put up the two register, the UCSRB and the UCSRC. So in UCSRC, if we are doing a character size of 8, these two bits have to be a 1, and this bit here, the UCSZ2, which is this one here, remember we're doing a character size of 8, so this has to be a 0. So this would be the combination. Now I put this one to a 1 because this is the transmit enable. The transmit enable, remember, is from UCSRB, so that has to be set to 1. The rest would be set to zeros. All right. Now we finally come to the USART bulk rate register. Basically, this is, as mentioned earlier, this is basically two 8 bits. So this one here, the UBBRL, all right, that is the low byte, and then UBRRH, that's the high byte. Although there are a total of 16 bits, but only 12 bits are used to set the USART bulk rate. Let's take a look at the programming steps. Now, the first thing is we need to enable the transmitter. Then step 2, set the number of data bits. Then step 3, set the bulk rate. Step 4, check the UDRE bit of the UCSRA register to ensure that the UDR buffer is ready for the next data. Then the character to be transmitted, that means the character that you want to send out, you have to load it into the UDR register. And then if you are sending more than one character, you go back to step 4 and repeat this until the message or the number of characters that you want to send is complete. Now let's take a look at the code. Okay, so let's look at the code. We have a few moments ago look at the programming steps. Let's see how that is put into practice. Okay, so those familiar with this programming with the ATmega 328 and those who have been following my video series, so This is the include directive to include this file because this file contains all the definition of the registers. Then there's the .csag, then the .org, the beginning of the code or the origin of the code. So remember, the first step is to enable the transmitter. So here I'm putting this binary pattern into R16, and then from R16 we copy that into UCSR0B. That's the register that we talked about earlier. Remember bit 3? We said bit 3, the transmitter enable bit has to be set to a 1. So that's what this is all about. And this is the hex equivalent. Now I've deliberately used the binary code so that later on, if you wish, you can refer back to these notes here to check this out. All right, so this 2 lines of code would enable the transmitter. Then this next 2 lines of code is to set the character size. As I mentioned, we're using 8-bit character. So remember, it's split into 2 registers, which is UCSRB and UCSRC. So UCSRC, these are the 2 bits that we want to look at. Remember, this has to be set to a 1. The UCSZ0 set to a 1. UCSZ1 set to a 1, and the UCSZ2, which is in the UCSRB, that is set to a 0, which is this 0 here. All right, this is a 0, bit 2. So the combination of these 2 will then set the character size of 8-bit, no parity bit, 1 stop bit. Next, this is this part here that will set the baud rate, and then this bit here will check the UDR, whether this is it empty, is it ready to receive the data. So these 3 bits here, these 3 instructions will do that. Then we load the character that we want to transmit. Here we want to transmit the character G, uppercase G, load it into R16. Then from R16, send it to UDR. That is the transmit buffer. Then this is the bit that would keep repeating this. So we keep sending this character G to the terminal. Okay, so we're in ATmega Studio 7. So I've uploaded the code here. So what I'm going to do is I'm going to walk you through using the single step function or step into function to see how this code actually works. And perhaps that would make things a little bit clearer. Right, so yeah, the first thing is I would like to do is to build the code. Now I've already built it several times, but I'll walk you through this whole process again. So build solution, at the bottom here you see build, 1 success or up to date, 0 fail, 0 skipped. So that's good news. Now to debug, first of all, we need to set this up properly. So if you could see this simulator button here, let me try and zoom in. Yes, so the simulation button here, let me zoom out and let me hit this button. You see another panel here appears under tool, which is this one here, which is highlighted. Make sure the select debugger / programmer, you have it on simulator. All right. Now, another way of getting hold of this panel here is if you go to this Solution Explorer, click on the file that we are supposed to debug. So in this case, it's serial com01. That's how I named my solution. So right click on this. Look for properties, which is at the end of this pop-up. Click it, and you get the panel. So there's two ways of getting to this panel. Make sure whatever method you use, make sure you're on the simulator for under tools. So let me just make sure you save it. If you make any what do you call changes, you will see an asterisk here. If you see that, then save it and then close this one. All right, so now we're ready for debugging session. So we already built the code. So go to debug up here and then start the Oh, before I do that, let me just go make sure you have this IO panel up. This can be gotten from here under debug, Windows, and IO here. All right, so let me go through it again. Debug, Windows, IO. All right, so now I have mine set up earlier. So make sure you have this panel. And okay, I think we're good to go now. So debug, start debugging and break. If everything goes right, you see the first line of code being highlighted with the arrow pointing to the line of code that will be executed. Now here also make sure you have the register panel, the process status. If you click on that one, that will show you the processor status. Register. Let's stick to register for the time being. So right, so we're good to go now. Beg your pardon. So I'm going to use the step into function. All right, under debug. So make sure your cursor is on the same line where this code is highlighted. So I will press on my laptop would be function F11. Now, before we do that, what does this instruction do? This instruction will basically copy this binary value. Usually I use hex code, which I highlighted here in the comment. So it's actually 08, but in binary that would be this one here. All right, this is the TXEN bit here. We'll see that in a minute. So load that value into R16, and then from R16 copy that into UCSR0B. The STS is store direct to data space. So basically you will store the contents of R16 into this register, which is UCSRB. All right, so without further ado, let's execute this line of code. Watch out for R16 here. All right, this bottom panel here. Let me just try and zoom in and see. Right, so R16 here. So watch out for that one. Zoom out. All right, so F11. Right, let's check R16. It's highlighted 08. That's what it is. Now, the next line of code basically will copy this content. It's not going to take this away. We will copy this content into UCSRB. Now, if I just to pull this down a bit, click on the USART, and you'll find the UCSRB here. So let me just adjust this a little bit so that we can see that. Pull this down a bit. Right, so I think we got enough space here. So UCSRB. Now we should see 08 All right, the binary value 00010000, which is 08. Watch out for that one. Make sure your cursor here is on this line, same line as the yellow bar. So function 11, yes, we get 08. All right, so yep, that would be, if you click on this minus button here, that will expand it. So let's just screw up, adjust this a little bit. Now 08 is this bit here, and it's highlighted here. That is the TXEN, that is the transmit enable bit. So that now is set, that's bit 4, set to a 1. Okay, so the next line of code now will load this value, hex value 06. That would load that into R16, which is here. Watch out for this one. All right, so we have 06 in R16. Then copy it to UCSRC. Now, let me just collapse this. So UCSRC is this one here. Open it up, expand it. All right, so now that is 06, right? So watch out for 0. Oh, it's already 06. Never mind, I think that was from my previous run. So anyway, you'll see. Yep. Now that would have set the number of bit, the data bits. That is 8-bit, no parity, 1 stop bit. And the first line, this first 2 line, let me just go back. That enable the transmitter. Now we set the baud rate here with 8 bits, no parity, 1 stop bit. Now, this next 2 bits here will set the, sorry, this, did I say baud? This will set the data bit, sorry. No parity, 1 stop bit. The next 2 lines of code here, that set with baud rate, and the baud rate I want to set is 9600. So the first thing is to load this 67, which is 011001111. We should see that in R16, which is here. All right, let's see, let's step into it. Yes, 67 is here. Now copy that into UBRRL. Where's that? Collapse this one. This is UBRR0. Watch this bit here. This is, remember this is a 2-bit register giving us 16 bits. So that's, watch out for that one. Yep, we've got 67. The upper byte is not used, only the low byte is used. So 67, that gives us a baud rate of 9600. All right, so the next one here, that will copy UCSRA, which is this contents of this, which is 20, to R20. So watch out for R20 here, which is this one here. All right. So copy that. All right. And then you have in R20 0 20 hexa. Now copy that. From there, we copy this. Oh no, it's not copying. The SBRS, that would that is the skip if bit in register is set. So we're testing for the UDRE bit, right? We want to check that bit. So now UDRB, where is UDRB? This is under A. UDRB, which is this one here. That check if that is set. All right. If it's not set, you skip it. If it's set, sorry. So if that is set, because this is set, it will skip it. Let me, SBRS stands for skip if bit in register is set. So the bit here is set, so we'll skip this instruction here, which takes us down here. I hope I'm not confused you. So load this character uppercase G into R16. We won't see G in R16. We will see the hexa equivalent. So watch out for R16. For 7, that is the hex equivalent of the uppercase G. Now we will then now copy that into UDR0. But watch what happens in this case here. We don't see anything. That I've tried this out with another simulator and I'm getting the same result. You don't see the contents of UDR 0 because my guess is I need to check this up. Remember I said this UDR is actually made up of the receive buffer and the transmit buffer, and the receive buffer and the transmit buffer each have a shift register. So in our case here, when you put this into the UDR buffer, it immediately gets loaded into the shift register. So I think that's what's happening, and that's why we don't see it. I've checked this out also with a hardware debug, and I'm getting the same result. Perhaps maybe if I find more concrete explanation, I would do a video on that. But for now, we don't see that in this register. It doesn't mean it is not working. I assure you it's working when I run this thing in real time. All right, so okay, now it will then jump back, in this case, into the beginning of this code here. All right, so function F11. Yep, and goes back. Now, we've gone through this in detail, each instruction. Now, the thing is, I'll run this thing now in without a single step. So let me just stop the debug. Now, to stop the debug, you can use this option here, or if you want to see this red button here, like this one, you can use that. So let me just use that. Okay, we stop the debug. Now, so what I'm going to do is I'm going to run this thing. I'm going to show you something else. Now, there is under tools, there's a debug visualizer. So go under tools, debug visualizer, and you will see this serial control panel. Now, if you don't see it, click on this button here, this right arrow, click on that one, then go under external connection, select, double click on serial port, close that again. Now with this one, you need to be connected to your Arduino Uno. All right, so make sure your Arduino Uno board is connected. Right now mine isn't connected, so I'll pause the video here and get my hardware. I'll come back soon. Okay, I'm back now. I just remember one more thing before we do this. Let's go back to our assembly code, and we've already compiled this. So, but we need to program the Arduino Uno with the code for this thing to work. So, sorry about this. I forgot to mention you need the hardware. That means you need to connect your laptop or your desktop to your Arduino Uno, and make sure that you know which port is connected to. If you're not too sure, you can use the device. Let me just open this up. Control panel. All right, and device manager. Look out for the the COM port. Mine is on COM 9, so let me just turn everything off. So when mine is COM 9, make sure everything is fine. Okay, so now I'm going to program the Arduino Uno with the code. So all right, so yeah, so mine's successful, is in. So let me just go back to the data visualizer. All right, now you can see the Arduino Uno is connected to COM 9. Now make sure the DTR, the open terminal, is checked. Once you're happy with that, you click on connect. And you can see the G's, the uppercase G is being printed on the terminal output panel. All right, so like I said, it does work despite not able to see the contents of UDR0 in this when we single step the code earlier. Okay, so we've come to an end to this video. I hope you'll find it useful, and in the next video I'll show you how to transmit a word and a message. And so why not join me in the next video? Thank you for watching. So bye.